Hello viewer, thank you for tuning in. Our project is classifying pneumonia in chest x-rays of COVID-19 patients by Avola, Kristen Cocciante, Amit Deb, and Joesph Henderson. The purpose for this project is to assist doctors in classifying pneumonia in lungs, as our models can look through unnecessary details in order to see important information more clearly. It would only be operating with the support of doctors who have a more technical understanding of the information portrayed in x-rays, while our model would pick up anything they might miss. Our data comes from the Cancer Imaging Archive and contains 998 chest x-rays from 361 patients. The x-rays are made up of 4 labeled categories: typical, atypical, indeterminate, and negative. Typical represents lungs containing the typical signs for pneumonia, which are certain levels of opacity in certain lobes of the lungs. Atypical represents lungs containing other abnormalities which aren't the typical signs for pneumonia, including pulmonary edema, lobar consolidation, etc. Indeterminate represents lungs which lack the typical findings of pneumonia, but do contain unilateral upper or central predominant distribution of airspace disease, which means there are levels of opacity in the lungs indicating airspace disease which are not similar to those seen in pneumonia. Negative represents lungs which do not have pneumonia. In our report, we will show how we have retrieved the data, separated it by patient, divided it out randomly into multiple variations of test and train, created rotated duplications to increase data to train on, and found the most accurate model to classify pneumonia in chest x-rays. I'll now pass it off to Joesph.
The data we're utilizing is sourced from the Cancer Imaging Archive, and the data set is composed of chest x-rays of patients who have opted into having their data shared. Due to the sensitive nature of the data and to preserve patient confidentiality, the data is provided to us in an anonymized form. Any identifying information relating to the patient is removed. The only information we have access to is their gender and their age at the time of the scan. The process of discerning which scan belongs to which category is somewhat complicated, but lends itself well to a scripting solution. The scan names and locations in the dataset can be cross-referenced between the annotation and clinical data files, each of which has a different set of information pertaining to different aspects of the scan. After parsing through these files, we're able to group our scans according to each patient. Our first approach was a fairly simple one. Take the scans, pool them all, and then sort them according to which label they belong to. These labeled scans are then divided up into a training set and a testing set. We put 75% of our scans in training, 25% in testing. While this approach is simple, it presents a major issue for the model. Since multiple scans for the same patient look very similar, having the same patient scans in both the train and test sets results in the model memorizing how the patient looks instead of recognizing meaningful features about their lungs. How do we fix this issue? The solution starts with how we structure sorting our scans. We'll sort the scans by patient, but then instead of pooling them, we'll label them while they're still grouped with the patient. We repeat this process for every patient. Then, instead of pooling the scans and performing our train and test split, we'll split along a similar ratio of patients. Then, we can safely pool the scans across their categories. This ensures that the model will never see a patient's scans in both the train set and the test set, meaning it can safely train on the data provided without the risk that it sees a scan in both sets. This process is referred to as leave K out or leave several out, where the majority of the patients are dedicated to training, while a certain number of patients, in our case 89, are left out each time the model is trained. While this concept of dividing train and test across patients helps to address the model memorization issue, there's another issue with the data. Across the 4 categories, negative scans are overrepresented. Of the total number of scans, about 3/4 of them are negative. Training the model on this data without any alterations leads to the model massively overpredicting negative scans. As you can see, this confusion matrix from our early phase of work on the project has nearly all predictions as negative. With so much negative data, the model predicts negative nearly every time. This can be deceiving, as the model accuracy associated with this matrix is around 75%, despite the model not producing any meaningful results. Luckily, our pre-processing pipeline helped to address this imbalance, along with many other aspects of the data. I'll hand it over to Amit, who will be able to explain in more detail.
Whew, Joseph, that's a whole lot of data. Now, let's get into how to process all this data you've given us. Before we even look at the contents of the data, we need to see the amount of data. As Joesph said, the data is a 75-25% split of patients. 75 is our training set, and respectively 25 is our testing set. Now we only care about the amount of images for the training set. I'll explain why we don't care about for the testing set. Since we are training on the train set, we need to normalize the amount of files to keep bias at a minimum. Why would bias be affected? If we had 600 negative for pneumonia x-rays and roughly 40 to 50 x-rays for the other categories, like Joesph said before, our model will predict everything to be negative even without the patient bias Joesph fixed. The test set is going to test the model if the model is working and does not adjust the weights at all, so testing does not need to be normalized. Now, how do we do that? Well, there are two things to do: filling and culling. In order to figure out what amount of files to fill and cull, we first need to double the amount of files in the smallest category. For example, if the smallest category, let's say atypical, had 49 files, at the end we would have 98 atypical files. Although doubling the amount of files isn't as simple as just copying the file with a different name. If we did that, then we would run into the same issue of having bias again, because we would be training on the same picture twice. What we have to do is data augmentation. If we randomly do a slight rotate of a float value between -4 to 4 degrees on an x-ray, it can simulate a doctor maybe scanning the x-ray slightly off. This will be enough for a neural network to discern the difference. The only problem is when rotating the x-rays is that the images will generate black sections like this. To fix this, we need this kind of math to get the max area of the image. Let's go back to the other categories to figure out whether they get filled or culled to the normalized amount. Categories that get filled are categories with their amount of files less than the doubled category amount. They use the same augmentation algorithm from before that was used in the doubling category. Rotate and get the max area. For example, if our negative category had 70 files in it, it would go to 98 files, equaling the atypical file count. Categories that get culled are categories that are more than the doubled category file count. They randomly get culled until it reached the normalized amount of files. For example, if our intermediate and typical categories had 100 and 300 files in it, they both would get culled to 98 to match the atypical amount of files. Now finally, all the training is ready to be processed, and now we can actually look at the data now. Clearly we can see they are .dcm files, but what exactly are they? DCM is shorthand for DICOM, which in itself is an acronym for Digital Imaging and Communications in Medicine. This file type was created in the late 90s. They're a standard file format for storing all sorts of medical images. But in our case, they're x-rays of lungs. They contain annotations and other data in them. Our TensorFlow neural network will definitely not be able to handle this data type. It can only handle NumPy arrays of NumPy arrays that contain images. So here's a couple ways to process these DICOMs for the neural network model. The first idea is that we can convert these files by taking their pixel value, convert them into PNGs. Then, when we run our model script, we can convert them into an NP array, process it, and load the images one at a time. The problem with this idea is that we'll have so many x-rays in each batch to process during the modeling phase that we'll either run out of memory before we even run the model, or it will take so long to load the images that it won't be practical to run multiple batches of images through the model. Now, how do we fix this issue? We gotta cut out middleman, i.e. the PNG. We take each DICOM, convert it to a NumPy array, and do processing. Processing entails changing the image to have values of 0 to 255, adding a color channel, converting it to unsigned int 8 and resizing the images to 299 by 299. Then we add it to another NP array. Here's the key part, is we save the NP array of NP array images to a specific NP file, so that we can load the batch of x-rays in the model anytime in a fraction of a second. That way we can only have to load the images once, and then we're done. We can keep using those images for the model and tweak our model as much as we want. Now let's hand it over to Andrew to wrap it all up.
Thanks, Amit. Now it's time to talk about our process of obtaining a working model and our path towards optimization. As a group, we decided that we were going to be using transfer learning with a pre-trained model well before we were going to obtain any splits of data. The main goal of this project is image classification, so we had a couple of options to pick from. At first, I had found ResNet 152, which showed promising accuracy through research. It wasn't until I had spoke to the professor outside of lab that I noticed a poster on the wall that had similar research that used a model named Inception v3, which looks something like this, which also brought in higher accuracies. So, after our first sprint, the model was staged and ready to go for the data to make its way through. During the downtime I had between researching which transfer learning model we were going to be using, and our scripts being completed for obtaining splits of X-ray images, I decided to research how to get my GPU to be compatible with TensorFlow. This became crucial to our development and testing process. The difference that this made in our project efficiency was astronomical. To put this into perspective, each epoch that would take around 3 minutes on our group's laptops only took around 4 seconds with TensorFlow's GPU compatibility. Once GPU compatibility was staged and ready to go, it was time to begin our path towards optimization. Amit and I worked in parallel for countless hours to make sure that the data we were going to pass through the model had the correct data types and was able to be preprocessed by Inception v3's preprocessing functions, like this. Time after time, I ran our scripts and obtained 10 splits of training and testing data. 3 of the 4 times, however, we had issues. These issues included the images were pitch black, the data types were incompatible with our model, or the images were not resized to the correct size. In this case, Inception v3 wanted 299 by 299 pixels, most certainly because the features would pop out more during our training stage. Finally, after 10 hours of running our final script, I obtained 10 proper splits of training and testing data. Now, it was time to run this data through our model and see how well it could be trained to detect different severities of pneumonia in COVID lung X-ray images. To our surprise, we hit 50% validation accuracy in our first of 10 splits of data. This was crazy for us because we had not yet optimized the model. After running our rest of the 10 splits of data, we obtained a crazy 90% validation accuracy. Now, it was on to my next task, optimization. We had heard through a classmate that there existed a function that would search the cross product of all hyperparameters in our model and spit out the best combination for the highest accuracy, called Grid Search CV. I ended up able to develop a script that would run our model. However, it didn't really meet our group's needs, considering it wasn't allowing us to change a different combination of units in our dense layers. Amit ended up finding a video about something called Keras Tuner, which did almost something similar to Grid Search CV, except we were actually able to change the units on our dense layers. After I had developed a script that would run our model through and find the best combination of those dense layer units, we ended up with a validation accuracy of 92% and training accuracy of 96%, which is exactly what we were looking for in the scope of time that we had. We ended up with a very impressive confusion matrix, and we were very proud of, as a group, of what we had accomplished. This is Andrew from the dorms, signing out.